Have you ever wondered why carbon can form four identical covalent bonds in molecules like methane? At first, it seems completely normal, but the moment you look at carbon's electron configuration, something doesn't add up. Based on everything we've learned so far, carbon appears to have only two unpaired electrons. So how can it possibly form four identical covalent bonds? Are we missing a piece of the puzzle? Or is there a hidden process happening inside the atom that completely changes the way chemical bonding works? Well, that's exactly what we're about to uncover. In today's lesson, we'll explore one of the most fascinating concepts in chemistry: hybridization. By the end of this video, you'll understand why atoms rearrange their orbitals, how hybrid orbitals are formed, and how to determine the hybridization of almost any molecule with confidence. So, let's dive in. To understand hybridization, we first need to understand the problem it was created to solve. According to basic atomic orbital theory, electrons occupy atomic orbitals such as s and p orbitals. Let's put that idea to the test using carbon. Carbon has 6 electrons, and its electron configuration is 1s2, 2s2, 2p2. Now focus only on the valence shell, because that's where chemical bonding takes place. Notice that the 2s orbital is completely filled, while the 2p orbitals contain only 2 unpaired electrons. Based on this arrangement, carbon appears to have only 2 unpaired electrons available for bonding. If that were true, carbon should form only 2 covalent bonds. But that's not what scientists observe. Take methane as an example. Carbon forms 4 identical covalent bonds, not 2. So the simple orbital model makes one prediction. But experimental evidence tells a completely different story. That means our model is missing an important piece of the puzzle. Before we can solve this mystery, let's quickly review the building blocks involved. The atomic orbitals. Every electron in an atom occupies a region of space called an orbital. An orbital isn't the exact path an electron follows. Instead, it's the region where an electron is most likely to be found. For hybridization, the most important orbitals are s, p, and in some cases, d orbitals. The s orbital has a simple spherical shape. No matter which direction you look at it from, it appears the same. The p orbitals are different. Each one has 2 lobes separated by the nucleus. There are 3 p orbitals: px, py, and pz. Each points in a different direction in 3-dimensional space. For elements in the 3rd period and beyond, d orbitals can also participate in hybridization. We'll explore those later when we study molecules with 5 or 6 electron domains. For now, remember one important idea. Hybridization happens when these atomic orbitals combine to form new hybrid orbitals. Now let's focus on another key concept. Not every electron in an atom participates in chemical bonding. Only the electrons in the outermost energy level are involved. These are called valence electrons. Valence electrons determine how an atom bonds, how many bonds it forms, and the overall shape of the molecules it creates. Let's look at carbon again. Its first energy level contains 2 electrons. These electrons stay close to the nucleus and normally do not participate in bonding. The second energy level contains 4 electrons. These 4 are carbon's valence electrons, and they're the electrons responsible for forming chemical bonds. Whenever we study bonding or hybridization, our attention is always on the valence electrons. Now let's connect everything we've learned. Let's revisit carbon's electron configuration. 1s2, 2s2, 2p2. The first energy level is completely filled. In the second energy level, the 2s orbital contains 2 paired electrons, while the 2p orbitals contain only 2 unpaired electrons. So based on this arrangement, carbon appears capable of forming only 2 bonds. Yet every carbon compound we've studied tells a different story. Clearly, something changes before carbon begins bonding. That change is called the excited state. Now watch what happens. Before carbon forms chemical bonds, one of the paired electrons in the 2s orbital absorbs a small amount of energy. That electron is promoted into the empty 2p orbital. As a result, carbon now has 1 electron in the 2s orbital and 1 electron in each of the 3 2p orbitals. Instead of having only 2 unpaired electrons, carbon now has 4 unpaired electrons. This means carbon now has the potential to form 4 covalent bonds. Problem solved? Not quite. A new question appears. These 4 orbitals are not identical. One is an s orbital, while the other 3 are p orbitals. So if the orbitals themselves are different, why are all 4 carbon-hydrogen bonds in methane exactly the same length and exactly the same strength? The answer lies in a remarkable process called hybridization, and that's exactly what we're going to explore now. So, what exactly is hybridization? Hybridization is the process in which atomic orbitals of nearly equal energy mix together to form a new set of identical orbitals called hybrid orbitals. But why would an atom do that? Think about what we just discovered. After reaching the excited state, carbon has 1 s orbital and 3 p orbitals, each containing a single electron. At first glance, carbon seems ready to form 4 bonds, but there's still a problem. These orbitals are not identical. An s orbital has a spherical shape, while p orbitals have completely different shapes and orientations. If carbon used these orbitals directly for bonding, we would expect the bonds to have different strengths and different lengths. But that's not what scientists observe. In molecules like methane, every carbon-hydrogen bond has the same length, the same strength, and the same bond angle. So how is that possible? The original atomic orbitals no longer behave independently. Instead, they combine to form a brand new set of identical hybrid orbitals. These hybrid orbitals have the same energy, the same shape, and the same ability to form chemical bonds. That's why carbon can create 4 identical covalent bonds. Now here's something important to remember. During hybridization, orbitals are mixed, not electrons. And here's another important point. The total number of orbitals never changes. If 4 atomic orbitals combine, they always produce 4 hybrid orbitals. Only their shape, energy, and orientation change. Once these new hybrid orbitals are formed, they overlap with orbitals from other atoms to create chemical bonds. Now that you understand what hybridization is, the next question is, how many different types of hybridization are there, and how can we recognize each one? Let's find out. Now that we know what hybridization is, the next question is, how many types of hybridization are there? The answer depends on exactly how many atomic orbitals participate in the mixing process. Let's look at them one by one. First, sp hybridization. In sp hybridization, 1 s orbital mixes with 1 p orbital. This produces 2 identical sp hybrid orbitals. To minimize electron repulsion, these hybrid orbitals arrange themselves as far apart as possible. As a result, they form a linear geometry with a bond angle of 180 degrees. Notice something interesting. Carbon originally had 3 p orbitals. Only one of them was used during hybridization. That means 2 p orbitals remain unhybridized. We'll soon see why those unhybridized orbitals are so important. Next, sp₂ hybridization. Here, 1 s orbital mixes with 2 p orbitals. This forms 3 identical sp₂ hybrid orbitals. To minimize electron repulsion, they arrange themselves in a trigonal planar geometry. The bond angle is 120 degrees. In this case, 1 p orbital remains unhybridized. We'll come back to its role in just a moment. Now, sp₃ hybridization. This is the most common type of hybridization. Here, 1 s orbital mixes with all 3 pi orbitals. The result is 4 identical sp₃ hybrid orbitals. They arrange themselves in a tetrahedral geometry with a bond angle of approximately 109.5 degrees. In sp₃d hybridization, 1 s orbital, 3 p orbitals, and 1 d orbital mix together. This produces 5 identical hybrid orbitals. Their geometry is trigonal, bipyramidal, with ideal bond angles of 90 degrees, 120 degrees, and 180 degrees. Finally, in sp₃d² hybridization, 1 s orbital, 3 p orbitals, and 2 d orbitals combine. This forms 6 identical hybrid orbitals. They arrange themselves into an octahedral geometry with ideal bond angles of 90 degrees. Here's an easy pattern to remember. As more orbitals mix together, more hybrid orbitals are formed, and the molecular geometry changes accordingly. But if you've been paying close attention, you may have noticed something interesting. In sp hybridization, two p orbitals were left unhybridized. In sp² hybridization, one p orbital remained unhybridized. So what exactly do those leftover p orbitals do? The answer introduces two of the most important types of chemical bonds, sigma bonds and pi bonds. So, what happens to those unhybridized p orbitals we just talked about? They don't simply disappear. Instead, they play a very important role in forming pi bonds. To understand this, we first need to know that there are two types of covalent bonds. Sigma bonds, represented by the Greek letter sigma, and pi bonds, represented by the Greek letter pi. Let's start with sigma bonds. A sigma bond is formed when two orbitals overlap head-on, along the line joining the nuclei of two atoms. Because this overlap is direct and more effective, sigma bonds are generally stronger than pi bonds. In fact, every single covalent bond contains one sigma bond. That means a single bond consists of one sigma bond. Now let's talk about pi bonds. A pi bond is formed by the side-to-side overlap of two unhybridized p orbitals. Unlike sigma bonds, the electron density is found above and below the line joining the two nuclei. Because this overlap is less direct, pi bonds are generally weaker than sigma bonds. Now let's put everything together. A single bond contains one sigma bond. A double bond contains one sigma bond and one pi bond. The first bond is always the sigma bond. The second bond is the pi bond. A triple bond contains one sigma bond and two pi bonds. Again, the first bond is always sigma. Every additional bond is a pi bond. Now remember what we learned earlier. In sp³ hybridization, all three p orbitals are used to form hybrid orbitals. That means no unhybridized p orbitals remain. As a result, sp³ hybridized atoms form only single bonds. In sp² hybridization, one p orbital remains unhybridized. That remaining p orbital can form one pi bond. That's why sp² hybridization is commonly associated with double bonds. And in sp hybridization, two p orbitals remain unhybridized. Those two p orbitals can form two pi bonds. That's why sp hybridization is commonly associated with triple bonds. Notice how everything is starting to connect. Hybridization determines which orbitals are available for bonding. Those orbitals determine whether an atom forms only sigma bonds or both sigma and pi bonds. Now comes the part that makes hybridization incredibly easy. Once you learn these simple methods, you'll be able to determine the hybridization of almost any molecule in just a few seconds. Now that we understand what hybridization is, the next question is, how can we determine the hybridization of an atom? Fortunately, you don't have to memorize every molecule individually. Chemists use a simple quantity called the steric number. Once you know the steric number, determining the hybridization becomes quick and easy. So how do we calculate the steric number? We use a simple formula. Steric number equals 1/2 multiplied by V plus M minus C plus A. Now let's understand what each letter represents. V is the number of valence electrons in the central atom. M is the number of monovalent atoms attached to the central atom. Monovalent atoms are atoms that usually form only one bond, such as hydrogen, fluorine, chlorine, bromine, and iodine. C represents the positive charge, or the charge on a cation. If there is no positive charge, simply use 0. A represents the negative charge, or the charge on an anion. If there is no negative charge, again, use 0. Now let's apply this formula. Take methane, CH4. The central atom is carbon. Carbon has 4 valence electrons, so V equals 4. There are 4 hydrogen atoms attached to carbon. Hydrogen is a monovalent atom, so M equals 4. There is no positive charge, so C equals 0. There is no negative charge, so A equals 0. Now substitute the values. Steric number equals 1/2 multiplied by 4 plus 4 minus 0 plus 0. That equals 1/2 of 8, which is 4. So the steric number of methane is 4. A steric number of 4 means the hybridization is sp³. And, as we learned earlier, sp³ hybridization gives a tetrahedral geometry. with a bond angle of approximately 109.5 degrees. Now let's solve a few more molecules. You'll notice that the process is exactly the same every time. Carbon dioxide, CO₂. The central atom is carbon. Carbon has 4 valence electrons, so V equals 4. There are no monovalent atoms attached to carbon. Oxygen is not a monovalent atom. Oxygen is a divalent atom because it usually forms 2 bonds. So M equals 0. There is no positive charge, so C equals 0. There is no negative charge, so A equals 0. Now substitute the values. Steric number equals 1/2 multiplied by 4 plus 0 minus 0 plus 0. That equals 2. So the steric number is 2. A steric number of 2 means the hybridization is sp. As we learned earlier, sp hybridization gives a linear geometry with a bond angle of 180 degrees. Now let's look at the ammonium ion. NH4+. The central atom is nitrogen. Nitrogen has 5 valence electrons, so V equals 5. There are 4 hydrogen atoms attached. Hydrogen is a monovalent atom, so M equals 4. The ion has a positive 1 charge, so C equals 1. There is no negative charge, so A equals 0. Now, substitute the values. Steric number equals 1/2 multiplied by 5 plus 4 minus 1 plus 0. That equals 4. So the steric number is 4. A steric number of 4 means the hybridization is sp³. Its shape is tetrahedral, with a bond angle of approximately 109.5 degrees. Now let's solve phosphorus pentachloride, PCl₅. The central atom is phosphorus. Phosphorus has 5 valence electrons, so V equals 5. There are 5 chlorine atoms attached. Chlorine is a monovalent atom. So M equals 5. There is no positive charge, so C equals 0. There is no negative charge, so A equals 0. Now substitute the values. Steric number equals 1/2 multiplied by 5 plus 5 minus 0 plus 0. That equals 5. So the steric number is 5. A steric number of 5 means the hybridization is sp³d. Its shape is trigonal bipyramidal, with bond angles of 90 degrees, 120 degrees, and 180 degrees. Finally, let's solve the sulfate ion, SO₄². The central atom is sulfur. Sulfur has 6 valence electrons, so V equals 6. There are no monovalent atoms attached. Oxygen is not a monovalent atom. Oxygen is a divalent atom because it usually forms 2 bonds. So M equals 0. There is no positive charge, so C equals 0. The ion has a negative 2 charge, so A equals 2. Now substitute the values. Steric number equals 1/2 multiplied by 6 plus 0 minus 0 plus 2. That equals 4. So the steric number is 4. A steric number of 4 means the hybridization is sp³. Its shape is tetrahedral, with a bond angle of approximately 109.5 degrees. Notice something interesting. No matter how different these molecules look, the process never changes. Simply calculate the steric number, identify the hybridization, and from there you can immediately predict the molecular geometry and the ideal bond angle. That's the real power of the steric number method. Now, you might be wondering, what if the molecule is already drawn as a structural formula like this? How do we determine the hybridization then? Do we still need to use the steric number formula every single time? The answer is, you certainly can, but there's an even faster method. It's called the sigma bond plus lone pair shortcut. Once you understand this technique, you'll be able to determine the hybridization of most molecules in just a few seconds. So first, let's understand how to recognize the different types of bonds. In a structural formula, each line represents a chemical bond between 2 atoms. One line represents a single bond, 2 lines represent a double bond, and 3 lines represent a triple bond. Now here's the most important rule. A single bond always contains 1 sigma bond. A double bond contains 1 sigma bond and 1 pi bond. The first bond is always the sigma bond, and the second bond is the pi bond. A triple bond contains one sigma bond and two pi bonds. Again, the first bond is always the sigma bond, while the second and third bonds are pi bonds. Now, here's the shortcut. When determining hybridization, we count only sigma bonds and lone pairs. We never count pi bonds. Why? Because sigma bonds and lone pairs determine the steric number, and the steric number determines the hybridization. Now let's see how this works. First, methane, CH4. Focus only on the central carbon atom. Carbon forms 4 single bonds with 4 hydrogen atoms. Each single bond contains one sigma bond. So carbon has 4 sigma bonds and 0 lone pairs. 4 plus 0 equals 4. A steric number of 4 means the hybridization is sp³, its geometry is tetrahedral, with a bond angle of approximately 109.5 degrees. Now let's move to the next molecule. Ethene, C₂H₄. We'll determine the hybridization of one carbon atom. Since both carbon atoms are identical, the answer will be the same for either one. That carbon forms 2 single bonds with hydrogen and 1 double bond with the other carbon. Remember, a double bond still contains only 1 sigma bond. The other bond is a pi bond, and we do not count pi bonds, so carbon has 3 sigma bonds and 0 lone pairs. 3 plus 0 equals 3. A steric number of 3 means the hybridization is sp². Its geometry is trigonal planar, with a bond angle of 120 degrees. Now let's look at our final molecule. Ethene, C₂H₂. Again, focus on just one carbon atom. That carbon forms 1 single bond with hydrogen and 1 triple bond with the other carbon. Remember, a triple bond contains 1 sigma bond and 2 pi bonds. We count only the sigma bond. So carbon has 2 sigma bonds and 0 lone pairs. 2 plus 0 equals 2. A steric number of 2 means the hybridization is sp. Its geometry is linear, with a bond angle of 180 degrees. Did you notice the pattern? Molecules with only single bonds are usually sp³ hybridized. Molecules containing a double bond are usually sp² hybridized, and molecules containing a triple bond are usually sp hybridized. Just remember one important point. Don't look at the entire molecule. Always determine the hybridization of the specific atom you're interested in. Now you've learned 2 powerful methods, the steric number method and the sigma bond plus lone pair shortcut. With these 2 techniques, you can determine the hybridization of almost any molecule with confidence. Thank you so much for watching, and I'll see you in the next lesson.